This video is on the objective, make predictions using a line of best fit. So we've seen how to find the best fit line for a scatter plot, or the regression equation, or least squares line, however you want to call it. All right, so now we're going to use that line to help us make predictions about possible future data. All right, so if you'd like to see more about the objective, click on More Instruction. I am going to actually show you some of those notes here. So, making predictions using the line of best fit. Well, we can use the equation of the line of best fit to make predictions about the set of data. Let's use the example about the first and third exam scores as an example here. So here, a random sample of 11 statistics students produced the following data, where X is the third exam score out of 80 points, and Y is their final exam score out of 200 points. Right? So each of these pairs is for a particular student, right? And there are 11 ordered pairs, 11 students here. The data is presented below in the table of values and represented with a scatter plot, right? So you see these 11 blue dots represented over here, where the x-axis is third exam scores and the y-axis is their final exam scores. The line of best fit, or the regression line, is graphed to the right as well, right? The light blue line running through here. And the equation of this line of best fit is given to us, right? Remember, the y hat equals 4.83x minus 173.51. Right, so slope, y-intercept there. Now, before we use the line of best fit to make predictions, we need to determine the significance of the correlation coefficient and whether this linear relationship between the variables is significant. So in this example, let's assume the R value is significant. Now this is, you saw me do this in previous videos. They're not going to have you do it here. But you remember taking the value of R and comparing it to some critical values, right, of R with so many degrees of freedom. It was, n minus 2, the number of pairs, points minus 2 degrees of freedom. And you compared your R to these critical values. If it was between the critical values, then you would say there was no linear relationship, and you wouldn't use this line as the best model as a predictor. If the value of R was outside the critical values, then you would say that there is a strong linear relationship between the variables, and then you could use the line to make predictions. And that was all talked about in a previous video and a previous objective, previous assignment. So we're not going to get into that here. We're going to assume that R is significant and that there is a strong linear relationship. Okay, so we're going to assume all that. We're going to assume that we can use this best fit line to make predictions. All right, so let's talk about the difference here between interpolation versus extrapolation. Now, interpolation is the process of predicting inside the observed x values. Right? The x values that are observed in the data, the actual, what's the lowest x value of all my points, and what's the highest x value of all my points, and making a prediction about what will happen for x values in between those, right? Inter is within, right? This results in reasonable and reliable predictions. So in the example above, right, the range of the x values is from 65 to 75. See, the lowest x value of any of these blue points is 65. The highest value of any of these blue points is 75. So if I use the line to make a guess, a prediction for the y value for any x value from 65 to 75, it'll be reasonable and reliable. So yeah, 65 and 75 into the equation. So substituting an x value between 65 and 75 into the equation of the line of best fit would be called interpolation, and will produce a reasonable and reliable response. And they give me an example here. I'll let you read the examples on your own. Now, extrapolation is the process of predicting outside of the observed x values observed in the data. So back up here again, right? The values that are observed, the x coordinates are from 65 to 75. So if I plug in x values, less than 65 or bigger than 75 into this equation, I'm doing what's called extrapolation. I'm making predictions about data that are outside my observed data. So again, in the example above, the range of x values is from 65 to 75. So substituting an x value above or below that range is called extrapolation. Extra means outer, outside, right? Extraordinary, right, is outside the ordinary and stuff like that. This can result in less reliable predictions. Since the value we are using is outside of the given data values, the likelihood that these values behave the same way is harder to predict than the values, inside my data. However, a less reliable prediction does not imply the prediction is unhelpful. Sometimes we can make less reliable but reasonable predictions, whereas sometimes the results are both unreliable and unreasonable. So I'll actually go over these examples here because these can be a bit confusing. So here's an example where I'm doing extrapolation, right? I'm plugging in a value outside my range of x values, and we get a less reliable but still reasonable prediction. So here, make a prediction using the line of best fit to determine the mean final exam score of statistics students who receive 77 on the third exam. So you see 77 is above the highest x value. So I'm doing extrapolation. I'm making guesses, predictions outside my normal range of data. So they do this, they plug 77 into the thing and they get 198.4. They guess that, they predict that this student, if a student scored 77 on the third exam, they'd score 198.4 on the final. Now, based on this equation, we'd be making a prediction that, again, they score 198.4 on the final on average. This result may be less reliable because it's outside our data, but since the final exam is out of 200, this could happen. So it is a reasonable guess. It has meaning. It could happen. So this result is less reliable, again, because my input was outside my range of data. I'm doing extrapolation. But it is reasonable because it can happen. Now, if it can't happen, then it would be an unreasonable guess. I hope that makes sense. Now, their example here. Make a prediction using the line of best fit, that same thing, to predict the final exam score of students who receive 90 on the third exam. Now, if you plug 90 in, you get 261.19. So your guess, you would say that you'd be making a prediction that students who earn a grade of 90 on the third exam will earn a grade of 261.19 on the final exam on average. Well, this cannot happen, right? The final exam is out of 200. So this is an unreasonable prediction, as well as less reliable, because you're doing outside, you're doing extrapolation. All right, so again, interpolation, extrapolation, right, and some more examples. And they even have a nice little graphic down here. This is when you look at more instruction after certain problems. See, they do a interpolation, reasonable predictions, extrapolation, they're more unreliable, and then maybe unreasonable, the reasonable, unreasonable, you really have to think about the problem. Like up here with this, the final exam score being at 200, sometimes your extrapolated guesses can be reasonable, but sometimes your extrapolated guesses can be unreasonable, right? You really have to think about the context of the problem. All right, so let's look at this example here. Pardon me. So here, Victor is studying the relationship between the average daily temperature and time spent watching television, and has collected the data shown in the table. Now they're already giving us the line of best fit, which is wonderful. All right, so I don't have to enter this in a table, in lists, and look at a graph and all that. Thing is, though, I will do that. All right, I will do that in a second. All right. So they give us the line of best fit for this data as y hat equals negative 0.81 times x plus 95.8. And we're supposed to assume the line of best fit is significant, right? So you found the value of r, the correlation coefficient, compared it to critical values, and determined that it was significant, that this linear model is a good model for our data. And there is a strong linear relationship between the variables. Okay, so you got temperatures and then their corresponding, number of minutes watching television when the temperature was that outside. Now there are only 4 pairs of data here. Right. And what I'm going to do, actually, like I said, I'll put this up on a calculator. All right. You don't have to do this, but I'm going to. All right, so I'm going to enter these lists. All right, so stat, edit, and then down list L1. I'll have the temperatures be my x coordinates, right? The independent variables, so 40. And there's not too many, so I'll let you watch me enter all the data. All right, so there's the 4 temperatures, and then their corresponding, the number of minutes watching television on days with those temperatures. So these will be the y coordinates of my points. All right, and then let's take a look at a scatter plot. So stat plot, turn it on. X coordinates are L1, Y coordinates are L2. I'm going to hit zoom stat. And here we go. Oh, look at that. That looks pretty darn linear, right? And they already told us this, right? They said assume that the line of best fit is significant and there is a strong linear relationship between the variables. And let me graph this line they gave us too, right? How about go to y equals negative 0.81x plus 95.8. And take a look at the graph of that line, and that looks like it fits that data pretty well. All right, definitely a strong negative linear relationship here. All right, well, I've got the equation y1 here. I've got the equation for my best fit line written in, so this will be nice. This will help me when I go to calculate some predictions. All right, so I'm going to take the calculator down for a second. And now they're asking us, they're saying, hey, part A, according to the line of best fit, what would be the predicted number of minutes spent watching television for an average daily temperature of 39 degrees? And round your answer to 2 decimal places. Now notice the range of temperatures here is from 40 to 70. 39 is not in that range. So what we're doing here is called extrapolation. Now I can go to my calculator. I'll pull this back up. All right, we can go to the main screen and just replace x here with this average daily. I'm replacing the x in the linear equation, the best fit line, with 39. Right, x represents these average daily temperatures. So I go negative 0.81 times 39, right, x, and then plus 95.8. and we're getting approximately, 2 decimal places already there, 64.21 minutes watching television. So the if the average daily temperature is 39 degrees, this predicts that the average person, or this person Victor, would watch on average on those days 64.2 minutes of television. Which that doesn't sound unreasonable. He's watching 64 minutes on 40-degree temperature days. Why not 64.2 on 39-degree temperature days? Now it's unreliable because it's outside our data, right? This is an extrapolated value, but it's not unreasonable, I wouldn't say, right? It's not like it came up 180 minutes all of a sudden. He's watching 3 hours of television when he was only watching 1 hour, at the 40-degree temperature days. Now I could have also done this. How I said in my y equals, I have the equation here. I can go to a table, just go second above the graph, it says table, and then go down to where it says 39. Now I would rather just have the table set up. I would rather have it, right now it's got the table set up where I put it, it has it for me, and I'd have to scroll down to 39 for x. I'd rather do this. Go to the table setup above the window, and down where it says independent, change that from auto to ask, and then go back to the table and you can enter whatever x value you wish. So I enter 39, and then you see 64.21, because that's what y1 was, the best fit line output. But either way, I'm getting 64.21, so that's what I'll enter here in the problem. So great, wonderful. Now notice it said that was part A, so I'm assuming there's going to be more to this. And there is, right? Part B. Is it reasonable to use this line of best fit to make the above prediction? Now I said it seemed reasonable because 64.21 wasn't that crazy compared to these other minutes, wasn't that extreme. It's unreliable, right? It's unreliable because it's extrapolated. The 39, the temperature of 39 was outside our range there. But I would say it's reasonable because it could happen. I can see this person, based on these numbers, I can see this person watching 64.2 minutes of television if they've already been watching 64, So like I said earlier, if this number came up as, 200 all of a sudden, I'd say, oh, based on these numbers here, I'd say that was unreasonable. That's probably not likely to happen. But the fact that it was so close, I'd say it was unreliable, but reasonable. All right, let's see what happens. Yeah. All right. Yeah, so they say this time is reasonable. Again, unreliable because we're extrapolating, but reasonable because the output, could happen. I believe it reasonably could happen. All right, then I think that's it. Yeah. All right. So I'll do another one like this in another video, but hopefully watching me here, going over the notes and the instruction, and doing stuff in the calculator, reading the more instruction when necessary, reading the answer explanations when they come up. I'm hoping all this stuff helps you out when you go over this material on your own. And thank you very much for watching.